Today, I'll demonstrate a hearing aid measurement using SoundCheck with some of our standard hearing aid test sequences. We'll use some of the tests outlined in the ANSI S3.22 hearing aid test standard: frequency response, input-output linearity, OSPL90, and release time. First, let's take a look at our hardware setup. It's a little more involved than something like a loudspeaker measurement because hearing aids have some unique test requirements. For a start, we need an anechoic test box. This one's a B&K 4232, but you can use anything similar. It has a speaker integrated inside, which we'll play our test signal out of. We'll put our hearing aid in this coupler with a 1/2-inch pressure microphone. We also have an SEM reference free field microphone, which is also going in the test box. The 1/2-inch mic needs LEMO power, so it's connected to a SoundConnect 2 power supply, and the mic input then goes into the AmpConnect 621 audio interface. The AmpConnect also provides power for the SEM mic and amplification for the speaker in the test box. If I were running the complete suite of ANSI S3.22 tests, I would also need a DC power supply and current monitor, but since the tests we're running today don't require voltage regulation or current monitoring, we'll just power the hearing aid from its internal battery. I've already calibrated the source speaker located inside the test box using my SEM reference microphone pointed at the source speaker. The coupler is configured with a 1/2-inch microphone capsule, and we'll attach our hearing aid to the coupler's input. We have some tack here to get a good seal. Now, we'll put it in the test box so its microphone port is located at the same position I had the reference microphone. Let's close the box and we're ready to test. Let's start with frequency response. The hearing aid should be set to its reference test gain. We'll play an equalized step sine sweep from 10 kHz to 100 Hz at a level of 60 dB SPL through the test box speaker, and then analyze the output of the hearing aid with a heterodyne algorithm to produce a frequency response. Next, the HFA, or high frequency average, is calculated by averaging the response values at 3 frequencies: 1000, 1600, and 2500 Hz. We then subtract 20 dB from the HFA, and 2 post-processing steps are used to find the upper and lower frequency points at which the response curve intersects the HFA minus 20 value. These are the high and low frequency cutoff points. Limits can be applied to all of the curves and values in this sequence. Let's run it. And here, you see the fundamental curve falls outside the upper and lower limits at a few frequency points. The low frequency cutoff is 217 Hz, and the high frequency cutoff is a little over 5K. Our next test is input-output linearity. We'll leave the hearing aid at reference test gain and use an amplitude sweep from 50 to 90 dB SPL played through the test box speaker. This is repeated at 4 frequencies, 1 to 4 kHz, and 1 kHz increments, and then the output of the hearing aid is plotted versus the input on the graph. This test is useful for characterizing any automatic gain control or compressor in the hearing aid, and is used to attenuate the hearing aid's output above a certain level so as not to further damage the user's hearing. So let's run it now. The effect of the automatic gain control is clearly visible at all 4 frequencies. The x-axis represents the stimulus level, and the y-axis is the output level from the hearing aid. We can see that the gain limiting kicks in when the input is in the 60 to 75 dB range, depending on the frequency, and note how the overall level of the 4 kHz curve is 10 dB lower than the others because the frequency response of the hearing aid is around 10 dB lower at that frequency relative to the others. The OSPL90 test measures the hearing aid's performance with an input signal of 90 dB SPL. For this test, we need to set the hearing aid gain to its maximum. An equalized step sine sweep from 8 kHz to 200 Hz is played at a level of 90 dB SPL, and then a broadband RMS response curve, which includes harmonics as specified in the standard, is analyzed from the recorded time waveform of the hearing aid's output. Next, the HFA, or high frequency average, is calculated by averaging the values at 3 frequencies: 1000, 1600, and 2500 Hz, and the max OSPL is calculated by finding the maximum point on the broadband response curve. Let's take a look. Okay. The OSPL90 curve looks much like the frequency response curve from our earlier measurement, and considering that the input to the hearing aid is a calibrated sweep at 90 dB, the amount of gain in our measurement is between 25 and 40 dB across most of the sweep range. The high frequency average from this measurement is 126.7 dB, and the maximum value on the curve is 129.7 dB. Lastly, we're going to measure the release time of the hearing aid. Again, we want the gain set to max, and we'll play a 2 kHz sine tone at 90 dB SPL for 1 second, then immediately drop it to 55 dB SPL for 2 more seconds. A band-limited time envelope to improve the measurement signal-to-noise ratio from 1.5 to 2.5 kHz is calculated and then run through a post-processing step to calculate the release time. That's the time the coupler SPL remains within 4 dB of the steady value for the 55 dB input. Here, we can see that the hearing aid output initially drops down to about 85 dB, but after 45 milliseconds, the release time is stabilized and the hearing aid maintains a steady output level of 115 dB. So that's 4 quick examples of tests from the ANSI S3.22 hearing aid standard. Of course, once we have the equipment for these, there are many other hearing aid tests that you can run using the same test setup, and you can configure tests for the complete ANSI S3.22 standard in SoundCheck. In fact, we've already done it, and we sell the test sequence package with all 20 measurements as an add-on to SoundCheck, so you don't even have to program it yourself. Please contact us to learn more.